In this video, I want to talk about model choice. That means I want to talk about steps 1 and 2 here. So step 1 was feature selection. So we have our predictor W1, and now I'm also allowing for the possibility of more than one variable that is used for prediction, and we are transforming these predictors into features x1 to xk. Once we have extracted the features, we have to decide how we want to use those features for prediction, and this is what we could call model choice. And so far there wasn't a lot of choice. What we've done is we've used OLS for prediction, so OLS on the features that we selected or that we extracted in the previous step. We fitted OLS on the training sample and then used the fitted coefficients to predict out of sample. So on the training set, we estimated the OLS coefficients, and then we applied them to compute predictions out of sample. This is pretty much the process as we've described it so far. So the only way for us to move along this x-axis and change the complexity of the model is to choose our features differently. Now we want to look at an alternative way of changing model complexity that works through manipulating model choice. So right now we only have this one choice here, and we want to fill in different choices of models. So what OLS does is that it approximates the conditional expectation. Approximates the conditional expectation, and conditional here means that we're using the information in the axis to improve our prediction, and that allows us to reduce bias. Now we know that OLS minimizes this expression, and this expression only cares about bias. So we know OLS is using information in the axis here to bring down bias, doesn't care about the variance, which will leave it usually somewhere in this overfitting part, where we care too much about bias and not enough about variance. OLS doesn't care at all about variance. So now let's look at a different model choice that doesn't care about bias but cares all about variance, and this one will be the sample mean. The sample mean on the training sample will predict always the sample mean on the training sample, irrespective of what axis we observe. And just to remind you what the sample mean is, so this is just the average over the y's in the training sample, and as you can see, this is all red, so the information in the out of sample observation, in the axis for the out of sample observation, isn't even used in the prediction. We always predict the same value regardless of what axis we observe. And this is because the sample mean estimates the unconditional expectation. OLS regression on k features will estimate k plus 1 coefficients, whereas the sample mean estimates only one coefficient, the sample mean. So this makes it so that the sample mean is typically estimated with very low variance, and OLS is estimated with a lot higher variance. On the other hand, OLS can use information that is observed to bring down the bias, and the sample mean cannot. So in other words, OLS is typically here, so low bias, high variance, and the sample mean is typically typically underfits. It has a high bias but a low variance. Let's write this down. OLS has low bias, high variance, and the sample mean has high bias, low variance. We can represent these two estimators also in a diagram where we put bias on the vertical axis and variance on the horizontal axis. Now OLS has a low bias but high variance, so it would be somewhere here. And the sample mean has a high bias but a low variance, so it would be somewhere here. Let's think about a situation where the OLS and the sample mean have the exact same prediction error. So that means the sample mean has to be on this 45-degree line that goes through OLS. So the sample mean would have to be somewhere here. If these positions describe the sample mean on OLS, then OLS and the sample mean have the same prediction error, but they arrive at this prediction error in different ways. So the OLS by having a low bias, and the sample mean by having a low variance. Since OLS and sample mean are good in orthogonal ways, it makes sense to wonder if we can just somehow combine them. So what happens if we take half the OLS prediction and half the sample mean prediction? So what I mean, let's take the OLS prediction and let's take the sample mean prediction, and we combine them by taking 1/2 of each. If we want to represent this combined prediction in our diagram, so we want to put it into the diagram, so where does it show up? It is tempting to think that since we are combining these two predictors, that we have to end up on the line segment connecting these two predictors in bias-variance space, and maybe even have to end up in the middle of this line segment. However, that is not true. Where we actually end up is below this line, somewhere here. What does that mean? Well, recall that all the predictive models on this 45-degree line have the same expected prediction error. Now models that are on the right hand side of this line have either a larger variance or a larger bias or both, so they have a higher expected prediction error. Similarly, all the models here have a lower expected prediction error. Therefore, the direction of this error gives the direction of models that are strictly preferred, and that means that our combined predictor is better than either of the two models that we used originally. The principle that is behind this improvement is called the principle of shrinkage. To understand this, note that our combined model consists of parts, like these two, that don't react to the axis in the out-of-sample observation, and a part here that reacts to sample observation. Through combining the two predictive models, we're making this part here, this is what allows us to have a low bias, we're making this part less important, right? When we're using all S, then the slope coefficients were beta 1 hat and through beta k hat, but now the slope coefficients in our combined model are actually beta 1 hat divided by 2, and all the slope coefficients divided by 2, so they are shrunken to be closer to 0. What we've done this way is that we have made a model that has a larger bias, right? So we've moved up from here to here in terms of bias, but also we've made a model that is easier to estimate and has lower variance. We've moved this way. And overall, so the gain through having a lower variance outweighs the loss from having a higher bias, and we end up in a better place. Here we have looked at an example where we combine two predictions by taking 1/2 of each prediction. Instead, we could have, of course, combined them in other ways. So for example, we could have taken alpha times the all-S prediction, where alpha is a number between 0 and 1, and then 1 minus alpha times the sample mean prediction. So if we had done that, then for alpha equal to 1, we would just be back at our all-S prediction, and from there on, if we decrease alpha slowly to 0, we would be moving kind of like this way. For alpha equal 1/2, we pass to this point. For alpha equal 0, we would be back at the sample mean. Now here, this traces out a sequence of models, and you might be wondering which one is the best model, what is the optimal combination of the two predictors, or what is the optimal amount of shrinkage. And it's you find the optimal of shrinkage obviously at the point where this curve is tangent to a 45-degree line. So probably something like this is the optimal amount of shrinkage. So this way we move to the difference curve, if you want, that is farthest into this direction of better predictive models. In this example, we have looked at the somewhat artificial setting where the sample mean and the OLS prediction have the same expected prediction error. And in that case, it is always true that you want to combine them, and that the models that combine the two predictions are superior to any of the two extreme points. However, if the sample mean and the OLS prediction don't have the same expected prediction error, then you may prefer either the pure sample mean or pure OLS, or a combination. And where you end up will depend on your population, it will depend on your predictive problem. The principle of shrinkage is not applied in practice like this. So people don't actually compute OLS prediction and sampling prediction and combine them in this way. A predictive method that is almost doing this is called ridge regression. So if you understand what we have discussed here, then you understand the intuition behind ridge regression and also other related penalized regression methods such as lasso regression. In addition, the idea that combining predictions from different predictive models gives us maybe superior predictions is very important in developing powerful predictive algorithms. And this is also sometimes called the principle of model averaging. And this principle is behind predictive methods that combine different predictive models, and such combinations of predictive models are called ensemble methods. The principle of shrinkage gives rise to new predictive models such as ridge regression and the lasso. Making statistical predictions is a very active research field, and it goes by a new fancy name. It's called machine learning. For the predictive problems that we've looked at so far, we have assumed that we have a training data set, and this training data set contains observations of the predicted outcomes. In machine learning, whenever we have such a training data set, then we say that we are facing a supervised learning problem. There are also methods for unsupervised learning, and these are mostly used in feature selection. All the predictive models that we've looked at so far, such as OLS, sample mean, and also ridge and lasso, are supervised learning methods. But when people think about machine learning, they often have even more complex models in mind, such as, for example, neural networks, boosted regression trees, or complex ensemble methods. We will not cover these methods in this course. However, many of the principles that we've learned so far, such as the bias-variance trade-off, also apply to them.